Now we can also represent vectors in the rectangular system. And we saw a picture of that already, but we can go into a little bit more detail here. So we're going to start by letting vector I be the unit vector whose direction is along the positive x-axis. So it looks like this. It starts at the origin and it ends at the point 1, 0. And then the vector j is going to be the unit vector whose direction is along the positive y-axis. So if we're going up to the point 0, 1 here, again, that starts at the origin and it goes to point 0, 1. So that is what we're defining as vector j. And by doing this, by defining these two units, we are able to actually write a whole bunch of different vectors in the rectangular system. So we can write the following. So let's say we have a different vector v that starts at the origin, but goes to a point AB instead. So for instance, right, maybe it starts here and then it ends here at the point P, which is, the values A, B. Well, what we can do is we can go ahead and we can use our unit vectors to help write this. And we do it as follows. So our vector is written as A times vector I plus B times vector J. A and B are both real numbers here, right? They represent that ending point, that terminal point. A is the horizontal component and B is called the vertical component. They are scalar components here. So they're being multiplied in. The sum together is called the linear combination. So it is a combining of the vectors, and we're using those original unit vectors and we're scaling them by these values A and B. And we can also find the magnitude of these vectors, and the formula is the square root of A squared plus B squared. So it's still using the distance formula, but because one of your points is the origin, it simplifies. So we have our vector here. So let's do a little bit of work with this so you can actually see some examples as well. So we're going to sketch this vector and we're also going to find its magnitude. So one thing you want to notice, this is your A and this is your B, right? So A is the horizontal component and B is the vertical. So this actually relates to the point A comma B. In this case is -3, 4. So what we're going to do to draw this is we start with our plane. And again, I'm just going to do a rough drawing here. I'm going to plot that point -3, 4, which is about right here. And you want to remember that of this form, you're starting at the origin. So the initial point is at the origin here, and that is your terminal point. So to go ahead and draw this, I'm just going to connect them. It's supposed to be a nice straight line there. And show the direction. And that's it. That is our vector. So the key thing is finding that A and B so that you know where that terminal point is. Now to find the magnitude, we use that formula, square root of A squared plus B squared. So our A here is -3. Make sure you're squaring your negatives in this case, which would be 9. And then 4 squared is 16. This is 25. So the magnitude or distance from the origin to the point -3, 4 is just 5 units. Now, not every vector starts at the origin, so we do have ways to account for that as well. So one thing to know before we move on is that a vector its initial point is at the origin is called a position vector. But of course, not every single vector is going to start that way. So we don't always start at the origin. So let's say we start somewhere else. So let's say we have vector v. With initial point 1 equal to x1, y1, and terminal point 2 equal to x2, y2 is equal to the position vector b equals x2 minus x1 I plus y2 minus y1 j. Now, remember, for equal for vectors, it means that they have the same magnitude and same direction. Okay, so that's what it means to be equal. So your vector could be somewhere else in the plane, right? Maybe it's shifted over, but we can sort of bring it back to the origin and then use what we already know. And it has the same magnitude and direction. So that's the key here. All right, so let's do an example. So let B be the vector from initial point P1 equal 3, -1, and to terminal point, so we don't need the word in there, P2 equals -2, 5. I want to write the vector in terms of the unit vectors, I and j. So basically, we're going to just sort of shift this vector. So the initial vector goes from 3, -1 to -2, 5. So maybe we can just draw that quickly just so we can see it. So 2, 5, 2. All right, so it goes from, let's see, 3, -1 to -2, 5. So this is vector v. But to write it in terms of I and j, we need to shift it to the origin. So that's really all we're doing here. And that's what this formula does for us. So we can also write it. I can subtract those x's. So let's see, x2, so -2 minus 3. And then I can subtract my y's. Just make sure you go in the right order. -2 minus -3 is -5. And then here, this become a positive, so I have 6. Now, if we're looking at the graph here, just to kind of see how these relate, this would give you the point -5, 6 as the terminal point and 0, 0 as the starting point. So -5, 1, 2, 3, 4, 5, and then 6 would be like right up here. And that's what that vector would look like. So you can see you're going in the same direction. It's the same length, same distance between those 2 points. It just really shifted over so that we can use it with those unit vectors instead. And then you could also use that to find the magnitude as well, because that formula is much simpler to use the formula when you have the unit vectors that you're using as well. Now you can also perform a lot of operations with vectors as well. So here we have 2 vectors, v and w. They're both written in terms of I and j, which is important here. And just to make it easier, for v, we're going to let the values have subscript 1, and for w, the values have subscript 2. Now, adding and subtracting vectors is actually very straightforward. If you're adding vectors, you just add the appropriate parts together. So the a parts that are with the I would get added, and the b parts that are with the j would get added. It's really sort of like combining like terms. And then for subtraction, do the same thing. You would subtract the a parts or subtract the b parts. Make sure you subtract in the correct order. That's really important. So if you're starting with a minus w, then b would come first for the number, and then you would subtract by the w value. So this is your adding, this is your subtracting. Now this here is your scalar multiplication. So multiplication. I apologize, my throat is very dry today. So here we're multiplying by a number. So we're not multiplying two vectors together. I guess I should actually put my vector symbols in, right? We're just multiplying by a number k there. So you multiply the A piece and the B piece there. And that's how you would go ahead and do those. So let's do a couple of examples here. So I'm just going to bring in two vectors. And let's start by adding them. So I have, for V, it's 5i plus 4j, and then for W is 6i minus 9j. Obviously, I, j, and V, W are all vectors. I'm not going to keep saying vector over and over again to keep it a little bit cleaner, but those have to do with the unit vectors here, I and j. So if we're adding them, we just add the associated parts. So I'm going to add the I parts together here. So you would have 5 plus 6, which is 11. And then you would add the j parts, 4 plus -9. So -5j, or of course you can rewrite that as 11i minus 5j is fine as well. We can subtract, do the same thing, just be careful with the order. We're doing v minus w, so you start with the v here. So for the I, the v is 5. And then over here it's 6. And then for the j part here, v has 4, and then minus -9. So I have -1i. Here, those two negatives will cancel, become positive, so plus 13j. You can leave the -1, but you don't have to. So this can just be -i plus 13j. Okay. Let's do some scalar multiplication. So let's say I want to do 6 times the vector b. So you're really just taking 6, and our vector is 5i plus 4j. And you can sort of just think of it as distributing, right? So you're doing 6 times 5, which is 30, and 6 times 4, which is 24. And I can also do negatives. I can do fractions. It doesn't matter. So let's just do a negative here, -3b. And again, you can really just think of it as distributing. So -15i plus -12j, and or -15i minus 12j is also fine there. And again, if you have fractions or decimals or anything else, they would just work with, just as usual, regular fraction rules, regular decimal rules here too. Now you can also do something more complicated. So I'm gonna use the same vectors. Let's say you want to find something that is 4v minus 2w. So here you have some scalar multiplication and you have subtraction. So just follow the order of operations. You would do the multiplication first and then the subtraction. So it'd be 4 times 5i plus 4j minus 2 times, and my w is 6i minus 9j. So I'm going to go ahead and do that multiplication first. And I would have 20i plus 16j. Here it'd be minus 12i. Careful, 2 negatives will cancel, plus 18j. Now you're going to go ahead and sort of think of it like combining like terms. I put the i's together here. I already incorporated the subtraction sign here, so I don't have to do it again because I used it with the 2. So I did a -2 distribution there, so it's already been included. So for my i's, I'm looking at 20 minus 12. And then for my j's, 16 plus 18. So 8i plus 34j. Okay, so we can make this more complicated if we need to, easier if we need to, and so on. A couple more notes here just about operations, excuse me. So you do have a 0 vector too. Don't overthink it. 0 would just be 0i plus 0j. So you do have the idea of 0 here. And just some other things to note, we have a lot of properties as well. So I don't want to write them all out here, but some things to note that make sense here, that you still have the commutative and associative properties for addition. So just like we have for real numbers, you can still move things around for addition. So the commutative and associative properties or regroup, those all still work here for your vectors as well. So commutative and associative property of addition, you have the idea of additive identity. So adding with 0 doesn't change anything. And you also have the idea of additive inverses. So if you have, something like 6i plus negative 6i, then that would cancel itself out of 0. So you do have the idea of additive inverses for vectors as well. For multiplication with scalar multiplication, you also have the associative property there. So you can regroup for the associative property with scalar multiplication. You have the distributive property as well, which we are basically already doing. You have the multiplicative identity, meaning if you multiply by a factor of 1, it doesn't change anything. If you multiply by 0, you still get 0. That is still true here. And then we have seen for magnitude with scalar multiplication already, where you just take the absolute value of that scalar multiplier and multiply it by the original magnitude. So we've seen that already. So there are some properties that you can still use here. A lot of what you already know is going to work and make sense. If you want to see the properties further in more detail, you can reference your textbook or go online and just Google it. I'll kind of just put it on the screen here for a second. If you want to pause and copy these down, that's perfectly fine. But again, a lot of it I think is common sense, right? With addition, you can still reorder, you can still regroup with addition. Adding with 0 doesn't change anything, and adding with a negative still cancel out. So that stuff is all going to stay the same. And then for scalar multiplication, again, associative property is fine. So you can, regroup for those scalar multipliers. We have the distributive property still, which we are basically using already. And then keeping in mind, multiplying by 1 doesn't change anything, and multiplying by 0 is still 0. And then that magnitude property we've already seen. So a lot of what you already know is going to just be consistent and continue, which makes vectors really